Well, hello again. In this example, you will learn how to do an approximate lateral analysis of a building frame using the portal method. We're going to look at this 2-bay frame and observe that portable approximate method, and the goal here is to generate moment diagrams for the beams and the columns. We are told to make a particular assumption, and that is that if we have an interior column, that it will take twice the shear that an exterior column will take. For clarification, you need to recognize that we have only one interior column that is present here. Two basic assumptions are used in a portal frame analysis. The first one we had already identified, in that the interior column takes twice the shear of the exterior columns, but also that the moment at the midspan of each girder and at each column is going to be 0. So what that means is we go ahead and insert moment releases here at mid-height of each of the columns, and then also at mid-span of each of the girders. We then need to assign the shears into each of the columns, and the easiest way for you to come up with that, whether you physically write it out or just envision it, think about making a cut through any particular story of your building. And then let's sketch a free body diagram looking at the upper portion. So we made a cut through there. We know that there is a load of 15 kips applied here. And what we are being told to do is make an assumption regarding the shear. Well, we don't have any interior columns here. These are both exterior, so those will take an equal proportion of that total shear. So 7.5 kips. 7.5 kips. That one was not an overly big challenge. However, what can be a little bit confusing is when we get to the next level down. So let's envision that we have a cut here. Let's go ahead and sketch the free body diagram for that. Looks something like this. 15 kips, 30 kips, and we are now being asked to solve for what these shears are, remembering that the center column must take twice the amount of shear as the exterior columns. The way I think about this is I look at the exterior column and give them a credit of 1, whereas the interior columns get a credit of 2. So let's follow through on this. 1, 2, 3, 4. So essentially I want to take my total shear, which would be this, at 45, and I want to divide it by 4. And that will give me 11.25 kips. Then I can come down here and I can assign the 11.25 kips to the exterior columns, and then the interior columns get twice that, 22.5 kips. And thus, you can take a quick look, that should sum up to be the 45. Very common mistake seen on this is that we will come in here and assign these shears to be just equal to 30. But be very clear that that does not cause equilibrium to exist. So knowing how much shear is in each of the columns, and knowing that we have these moment releases, wherein we know where the moment is equal to 0, we can use that to our advantage now as we start running statics and solving for the internal forces within this frame. So we will essentially just cut this frame apart. What we want to do is completely isolate each of these individual structural pieces. So let's look at that segment up near joint A. Here is the free body diagram for that. We should know that the internal shear is 7.5 kips. And then we have an internal axial, NAC, VAB, NAB. That's my complete free body diagram. You'll notice if I had not made any assumptions regarding shear in the columns, I would have had 4 unknowns on this free body, and that would have been an issue for me. However, I've only got 3 unknowns, and I do have a total of 3 equations of equilibrium. So I'm going to run through this on the first one. Sum of forces in the x is equal to 15 kips plus NAB minus 7.5 kips, and all that's equal to 0. So NAB is equal to negative 7.5 kips, and since that is negative, that will be in compression. I'm then going to sum the moments about joint A. That'll give me negative VAB multiplied by 12.5 feet minus 7.5 kips multiplied by 6 feet, and that is equal to 0. So VAB is equal to negative 3.6 kips. And then lastly, sum of forces in the Y will give me negative NAC minus a negative 3.6 kips equals 0. So NAC is equal to 3.6 kips. And since that is positive, that will be in tension. Once I get that information, I can then go over to joint B. You'll notice on this free body diagram I've taken whatever my knowns were and have translated them over. So this came from my previous analysis, and this came from the assignment of shears into the columns. So that really left me with one unknown on this, NBD. And I could get that by summing forces in the Y direction equal to negative 3.6 kips minus NBD equals 0. NBD is equal to negative 3.6 kips. And since it's negative, we know that that's in compression. We move right along, and we can solve for the remainder of the unknowns as we look at joint C. And then we run equilibrium, and that will reveal that NCD is a negative 26.25 kips, the shear in CD is negative 9 kips, and the axial in NCF is 12.6 kips in tension. Moving on to joint F, we get the free bodies looking like this. Remember, all we're doing is we're taking the knowns from the previous diagrams and translating them over, and then running equilibrium to solve for the remainder of those unknowns. We then go on to joint E, recognizing here that this is an indication of compression and this is an indication of compression. And then we move on to joint H and run those equilibrium equations there. One thing you'll notice is I had skipped over joint D, and I had done that simply so that I could minimize the number of unknowns I had on that. But you can go in whatever order you want as long as you don't have more than 3 unknowns on any free body diagram. And that's what we've done here, is we then had to go to every single joint to make sure we had the complete responses in all of these. So it's a little bit like truss analysis, joint to joint to joint to joint. And you simply need to separate the structure out by cutting at all of the moment releases and breaking them into their individual free body diagrams. The next thing we need to do is be able to generate the moment diagrams from all of these internal forces that we have found. And you can take a look back at the original structure and recognize that we only have point loads being applied at the joints. There's no distributed loads on any of the members, and so what that means is that our moment diagrams become very simple and easy to generate. We know that at mid-span and at mid-height the moment is 0, and so all we need is we need to know what the moments are at the ends of the members themselves. And I'm going to demonstrate that here. If we were to make a cut at point A, we would then have unknown internal shear and an unknown internal moment. I can then sum moments at point A for that particular free body diagram. Give me negative MA plus 3.6 K times 12.5 feet equals 0, so moment at A is equal to 45 kip feet. And that is a positive, meaning I assumed the correct direction. Let me show you how that translates over here to the moment diagram. I'm going to sketch this as a complete structure. Units of kip feet will be used. What we know is that at point A, the moment here is 45, and we also know that at midspan it is 0. Since there is no distributed load, this becomes a linear line. And if you wanted, you could go ahead then and go through the entire structure and generate the moment diagram just like this, recognizing that at mid-span and at mid-height we know what the moments are there at being 0, and go through it piece by piece by piece. But what you will quickly find out is that all these moment diagrams for each girder are anti-symmetric, meaning it'll come down here into this negative 45. Let me show you one more free body diagram just to kind of drive this point home. Look at joint D, and then you can very quickly take these shears, multiply it by their moment arm, and you can get what these internal moments are. This is 45. You get 5.4 multiplied by 12.5, and that'll be 67.5. You take 9, multiply it by 12.5. This will give you 112.5. Take 22.5, multiply it by 6, and you'll get this at being 135. So let's take a look back here at our moment diagram and see what that actually tells us. It tells us that we've got a moment diagram here that is 45. And you're just going to have to decide which side of these lines you're going to call positive and which side you're going to call negative. For the column, I will call the left side positive, the right side negative. Then we've got here 135, negative 135. You notice how those magnitudes are always the same on each of the columns. We've got for the girder, got a moment diagram coming back here, 67.5, negative 67.5. For this girder here, 112.5, negative 112.5. And then just in a like fashion, you go ahead and get those moment diagrams for your columns. Looks something like this. 67.5, negative 67.5. And that actually completes the entire moment diagram. So the key was here is you have to think about this process. You know what the moments are at mid-height. You simply need to find out what the moment is at the end of each member by taking internal shear multiplied by its moment arm. That concludes this example. As always, it's a beautiful day for studying structures.